When someone asks me what I do for a living and I say finite element analysis, the conversation usually stops there. Most people know what a doctor, lawyer, or accountant does, but not an FEA analyst. So in this video, I want to make clear what FEA is and why it matters. To explain FEA, we need to go back a bit. Before computers were cheap and fast, engineers developed the parts mostly by testing. The designer developed the part, then it was manufactured and tested. If the part failed, it was redesigned and tested again and again. The part might fail in one place and after redesign in another. This cycle repeated until the part survived the required number of load cycles. This process worked, but it was slow and expensive. Making a prototype, setting up the test, and running it could take weeks or even months. Some teams took a more simple approach, making a part thicker and bulkier. The part might not break, but it becomes heavier and more expensive. This trade-off depends on the application. If you are making a part for a factory line and you need it as soon as possible, adding some extra material might be acceptable. But in motorsport, every gram matters. In aerospace, you just can't simply make parts heavier. The plane won't fly. So in these applications, you need more sophisticated approach. That's where finite element analysis, FEA, comes in. In plain terms, FEA is a way to simulate how a part will behave under loading. Here is a basic workflow. You start with the geometry from the designer. Then you divide the geometry into a mesh. A lot of small, simple elements, like tetrahedrons, hexahedrons, or similar shapes. Those are the finite elements, and that's where the method gets its name. You assign the material properties, is it steel, aluminum, or plastic, and then you define loads and boundary conditions, how it's supported, what forces act on it, and where it contacts with other parts. After this setup, the algorithm computes approximate solutions for each tiny element and combines them. The result gives you a map of stress, deformations, temperatures, contact pressures, or reaction forces, almost any physical quantity you care about. The huge advantage is obvious. You don't need to manufacture the part or set up a physical test to see how it behaves. It saves time and money, and lets engineers explore many more design options fairly quickly. But, and this is important, FEA isn't magical, and your outputs are only good as your inputs. Some people say garbage in, garbage out, and that is true here. Numerical methods behind FEA are based on solid physics and mathematics. With a proper model and mesh quality, the method itself is reliable, but some inputs may cause the error. Material data. Real mechanical properties depend on the process, how it was manufactured. If you have two parts from the same material but from different suppliers, they will most likely behave differently. The datasheet helps, but the process behind it still matters. Loading and boundary conditions. If you don't model how the part is actually supported or loaded, your results won't match the reality. Contacts and interfaces. Modeling touching over two parts and how the load is transferred is tricky, especially because of friction behind them. Simplifications. Sometimes analysts simplify geometry or connections to save computational time. It's fine, but you need to be aware of what you're leaving behind. And finally, as I've mentioned, mesh quality. Too coarse mesh can miss stress concentration, but on the other hand, too fine mesh can increase cost and computational power. You need it perfectly balanced, as all things should be. A good FE analyst recognizes these limitations and questions the inputs. Experience helps estimate whether boundary conditions are realistic or whether material data is trustworthy. So, what's the practical approach? Don't treat FEA as a replacement for physical testing. Instead, use these two together. FEA helps you narrow the design space and reduces the number of prototypes. Tests then calibrate and validate your model. Once your model matches the test data, it can be trusted more and used for further design improvements. This combination, simulation with the targeted testing, is the sweet spot. If you should take only 3 things from this video, let them be: FEA reduces cost and development time by testing the design virtually. It cannot be 100% trusted because input data can be imperfect. FEA should complement the physical testing. It should not fully replace it. And that is everything for today's video. Thank you for listening until the end, and let me know in the comments if this was your first time hearing about FEA or you have seen it in your studies or work already. If you want to see FEA in action, definitely check my video about stress concentration. Have a great day and see you in the next video.